back to the next lecture of Module 2, Mathematical Modeling. Let's first have a recap of what we had planned for this module. We discussed the conservational laws of the physics, and we discussed notations and mathematical preliminaries. We had planned to cover the derivation of governing equations of fluid flow, and in today's lecture our focus would be on continuity equation, that is what we call mass conservation equation. The next two topics, broad topics, are mathematical classification and boundary condition of flow problems, which we would be taking in subsequent lectures. Now let's have a recap of what we discussed in the last lecture. We had discussed outline statements of conservation laws of fluid dynamics. We just briefly outlined what we mean by the conservation of mass for a continuum system. Then we discussed Newton's second law of motion, which gives us what we call momentum conservation. We also talked about energy conservation and the constitutive relations which we require for the modeling of different materials. Then we discussed different types of mathematical notations which are commonly used in CFD. We saw in a given reference frame how do we write our equations for a given physical law in expanded form, which would give us an equation linked to a specific reference frame, Cartesian, polar or cylindrical polar. We also looked at what we call coordinate free form or dyadic notation, and we looked at Cartesian tensor notation and different conventions which we use for use of this very simple and concise Cartesian tensor notation to represent our mathematical equations. Then we discussed two theorems. The first one was Gauss divergence theorem, which we said we are going to use primarily for changing volume integrals into surface integrals and vice versa. And the last theorem which we discussed was what we called Reynolds transport theorem, which allows us to change the quantities expressed for what we call a control mass system into a control volume based representation and vice versa. We will have a brief recap of our Reynolds transport theorem because this is the one which we are going to use very often today and in the next few lectures. Let's say that we have got an extensive property, capital phi. Capital phi could be mass, it could be momentum, or it could be energy, and the corresponding intensive property, that is property per unit mass, that we denote by small phi. So the capital phi is defined as the volume integral of rho phi d omega. Now the statement of Reynolds transport theorem was that rate of change of phi for the system, that is d phi by dt, for this control mass system, that is the system whose mass is fixed, it consists of two parts when we represent it in terms of the integrals for the control volume. The first one is the time derivative of the content of capital phi in the control volume, that is rate of change of phi in the control volume. This term we also represent as temporal derivative, and we can simply say that we can denote it as del capital phi subscript Cv by del t, plus we have to add what we call the net flux of phi through the control surface, that which is represented by an integral over the control surface of rho phi v minus vc dot dA, where vc is the velocity of a chosen reference frame. So the second term on the right hand side essentially represents what we call net flux of phi through Cs. We also call it as convective term, and we can use it another notation for it. We can say this is capital phi dot out. So essentially what Reynolds transport theorem says that, look, if you got a quantity capital phi, is time rate of change for a control mass system is equivalent to temporal derivative of phi for a control volume plus the net efflux rate of phi out of the control surface, and this is the one which we are going to use in the derivation of continuity equation, derivation of momentum equation, and the derivation of energy equation subsequently. Now in today's lecture we would focus on our mass conservation equation, which gives us what we frequently call continuity equation in fluid mechanics, and this is the outline of today. We will first have a brief review of kinematics, that is the different notations or terms which we use in kinematic description of the flow. Some of these terms would be useful in the representation of our conservation laws. Then we will have a look at integral versus differential forms. We will derive in today's lecture as well as in subsequent lectures integral form as well as differential forms. Where do we need both of these forms? We will discuss briefly about these two, and thereafter we would obtain the integral form of continuity equation for an arbitrary control volume, or what we call arbitrary domain. And next we would use mathematical jugglery to obtain differential form of continuity equations starting from the integral form. We will also obtain differential forms based on a simple differential control volume, and this way we would put a full stop to today's lecture. And now let us start with a review of kinematics. We will have a look at how do we define linear strain rate, volumetric strain rate, and rate of shear. Now before we proceed for definition of these terms, let us have a look at one particular derivative which is referred to as material derivative. How do we define a material derivative and what we mean by it? Material derivative is useful in the fluid mechanics in the context of what we call Eulerian description of a flow. So suppose we have got any filled quantity which is function of our x1, x2, x3 spatial coordinates and time. A function defined for a given fluid domain now. How do you find out the rate of change of f with respect to time? So now we can use the basic law of calculus, and change in f can be represented as, let us call this differential change is small df. This is del f by del t, that is partial derivative of f with respect to time into the small time increment dt plus del f over del x1 dx1 plus del f over del x2 dx2 plus del f over del x3 dx3. So now what would be the rate of change of f with respect to time? Change of f following a material particle of fluid. This would be given by df by dt, and this would simply become del f by del t, the dt goes off, plus del f over del x1 dx1 by dt plus del f over del x2 dx2 by dt plus del of over del x3 dx3 by dt. But now let us recall the way we have defined our velocities. So the velocity component v1 is actually dx1 by dt. Similarly v2 is dx2 by dt, and v3 is equal to dx3 by dt. Therefore our df by dt, this becomes del f over del t plus v1 del f over del x1 plus v2 del f over del x2 plus v3 del f over del x3. Let us write it a bit more concisely using our tensor notation. So, df by dt is equal to del f by del t plus Vi del f over del xi, or in vector form we can express it as del f by del t plus V dot del f. So, that is the expression for the rate of change of f following a material particle, and that is why we call this as material derivative. We can extract this derivative operator d by dt, and this could be written as del by del t plus Vi del over del xi, or equivalently as del by del t plus V dot del. So, this is our material derivative operator, which essentially tells us the rate of change with respect to time for a material system. Next, let us have a look at the strain rates which we would frequently use in the description of the fluid motion, and first let us concentrate on what we call, how would we define linear strain rate. It would be worthwhile to note that in fluid mechanics we do not talk about a strain per se, because that is meaningless in the for a fluid medium. So, we always talk about in terms of the rate of linear strain or rate of shear strain. Now, how would we identify or how would we define this linear strain rate? Suppose we have chosen our Cartesian reference frame x1, x2 and x3. Our velocity field is given by V as a function of x and t. Now, the velocity vector V can be expressed in its component form V1 I1 plus V2 I2 plus V3 I3, where these I1, I2 and I3, these are unit vectors in x1, x2 and x3 directions respectively. Let us just define the rate of linear strain in one direction. Let us choose x1 direction, and suppose we take a very simple linear element. So, let us choose a small linear element of an infinitesimal length delta x1. Let its ends be denoted as a and b. So, x velocity of end A, let us call it as V1, then we can use Taylor series expansion and obtain the velocity at point B, which is situated at a distance delta x1 to the right as V1 plus delta V1 over del x1 delta x1. Now, this is the position of this small linear element at time t. After a small time increment t plus delta t, this element would have moved to the right under the influence of x velocity component. Now, let us say the change position is a prime b prime. Now, this a prime b prime, that represents the changed element AB at time t plus dt. How would we obtain the position of A prime? That is very simple. The difference between A and A prime would be given by V1 dt. Similarly, this difference between B and B prime, that can be easily obtained as V1 plus delta V1 over delta x1 del x1 times dt. Okay. Now, can we obtain what is the length of segment A prime B prime? So, length of fluid element A prime B prime, this is simply equal to B prime plus AB minus A prime. That is, this is equal to delta x1 plus V1 plus del V1 over del x1 delta x1 times dt minus V1 dt. So, if you simplify it, we get this is equal to delta x1 plus delta V1 over delta x1 delta x1 dt. So, hence what is the change in the linear scale or length of the segment AB? Change in the length of segment AB this is equal to A prime B prime minus AB, which becomes delta V1 over delta x1 delta x1 delta t. So, now we can define our linear strain rate. So, linear strain rate in x1 direction, which is given by the time rate of change, that is 1 by dt of change in length, that is A prime B prime minus AB divided by the original length AB. So, if you do that, we would essentially get delta V1 over delta x1 delta x1 over delta x1 dt by dt. It is nothing but delta V1 over delta x1. We can use a symbol small e to denote what we call a strain rate tensor. So, E11 can be expressed as delta V1 over delta x1. Now, this can be generalized, and we can say that linear strain rate in any direction, any coordinate direction xi, that can be represented as, or rather in direction x alpha delta V alpha over delta x alpha, and here we would not use no summation over alpha. If you go back to a solid mechanics class, what we learned is that volumetric strain rate is nothing but the summation of the rate of normal strains in 3 mutually perpendicular directions. suppose we take a small volume, let us call it as delta V. Now this delta V can be given by delta x1, delta x2, delta x3. So how do you define volumetric strain rate? Volumetric strain rate, that would be given by 1 by dt, or rather d by dt of delta V 1 over delta V. So this is 1 over delta x1, delta x2, delta x3 d by dt of delta x1, delta x2, delta x3. Now we can expand the terms and we can easily see that this is equivalent to delta V1 over delta x1 plus delta V2 over delta x2 plus delta V3 over delta x3, or in other words, if you use a symbol E subscript V dot to denote our volumetric strain rate, this is given by del V1 over del x1 plus del V2 over del x2 plus del V3 over del x3, which we can easily identify as the divergence of velocity field. Okay, so our volumetric strain rate for any fluid element, that is simply obtained by finding out what is divergence of V at a given position. Next important quantity is what we call rate of shear or shear strain rate. Now for this we have to consider a small rectangular fluid element and find out what is the rate of change of the angle between two line segments. Suppose we call these segments as AB and AC, which were initially perpendicular. What happens to these segments? What happens to the change in the angle as this fluid element deforms under the effect of the velocity field? Suppose new position of these elements is given by A prime, B prime and C prime. So on the left hand side, this we have the position at time t. Now here we have got the position at time t plus dt, where dt is infinitesimally small time increment. Now we can identify two angles. The change with respect to the horizontal of the line segment A prime B prime, let us call this small angle as d alpha, and this again change from vertical AC, which was initially vertical, now it has become inclined, let us call this angle as d beta. So what is total change in the angle from 90 degree? So total change in angle, this is given by d alpha plus d beta. So now we can define the rate of shear or shear strain rate we normally use symbol gamma for shear strain, and for rate let us put a small dot over it. So, gamma dot x1 x2, okay, that is what we had initially said, AB is along x1 direction and AC is along x2 direction. This would be defined as d alpha plus d beta by dt. D alpha plus d beta, that represents the net change in the angle, and its time rate we can obtain by dividing it with respect to dt. Now let us see how we can obtain d alpha and d beta separately, and for that we need to have a look at the change in the positions. A shifts from A to A prime, and this shift would be given by that v2 velocity component at point A, this is v2 times dt. How much would be the change in B? This change can be obtained if you look at the v2 velocity at B. So, this will be given by v2 plus del v2 over del x1 delta x1. This would be the velocity at point B. So, v1 and v2. At point B we have got the velocities, v2 velocity would be given by Taylor series expansion as v2 plus del v2 over del x2 delta x1. So, let us use that velocity, this multiplied by dt. So, now can you find out what is d alpha? D alpha would be v2 times v2 plus del v2 over del x1 delta x1 times dt minus v2 times dt, or in other words this is equal to del v2 over del x1 delta x1 times d. In fact, d alpha would be it's an angle, so we have to divide it by the arc length, which is delta x1. This whole thing multiplied by 1 over delta x1. So, hereby we obtain d alpha is equal to delta v2 over delta x1 dt. Similarly, we can obtain the expression for d beta. So, d beta would be given as delta v1 over delta x2 times dt. So, therefore, our gamma dot x1 x2, this becomes del v1 over del x2 plus del v2 over del x1. In fact, we can now generalize it for any pair of the directions, that is we can write gamma dot xi xj as del vi over del xj plus del vj over del xi. So, this is expression for the rate of shear along two mutually perpendicular directions. Next, can we define what we call strain rate tensor? Looking at the two previous definitions which we had, we can define as a strain rate tensor. Now, there are different symbols used. We very often people use symbol capital S, or some people prefer to use small e. So, this can be represented as half of del Vi over del Xj plus del Vj over del Xi. So, you can easily verify that a expression for linear strain rate which we have defined earlier, or the shear strain rate, these two are identical. That is, we can easily establish that Eij is half of our gamma ij dot, I is not equal to j, and similarly Eij, sorry, Eii or E alpha alpha, this becomes del V alpha over del X alpha, no summation over alpha. So, in the tensor form or dyadic notation, we can write S or E as half of gradient of velocity vector plus the transpose of the gradient of velocity. So, this is whatever shear strain, sorry, or strain rate tensor looks like in terms of the gradient of velocity vector. Okay, now next let us come back to a mass conservation equation or a continuity equation. We know from the basic physics that mass of a system is conserved, that is to say, if capital M represents the mass of a system, its time derivative has to be 0. Now, how do you define mass for an arbitrary volume omega? So, M is defined as volume integral of rho into 1 d omega. Now, we can identify, if we compare this definition of mass with the intrinsic and extrinsic properties which we had introduced earlier in definition of Reynolds transport theorem, we can clearly see that phi, capital phi is same as capital M, and small phi is equal to 1. So, if we go back to our Reynolds transport theorem, see Reynolds transport theorem for a quantity capital phi was d capital phi over dt for the control mass. This was given as del by del t of Cv rho small phi dV plus the surface integral of rho phi V dot dA, and this holds true for an arbitrary control volume, and Cm can be identified as the system which is occupied or which occupies this control volume at any time instant capital T. Now, we have already identified our capital phi is identical to M, and a small phi, that is our intrinsic property in this case, becomes 1 because M is defined as rho d omega, or we can say that this is rho into 1 d omega. So, now we can put, let us put small phi is equal to 1 on the right hand side, and what we get, that dm by dt for a control mass system, this is equal to del by del t of rho dV plus the surface integral rho v dot dA. So, now we have obtained the rate of change of mass for our control volume, and we can now put it in the expression for this mass conservation equation dm by dt Cm is equal to 0, and we get this particular form for mass conservation equation. And this is what we call the integral form of mass conservation or continuity equation. It is given as del by del T of rho d omega over Cv plus the surface integral rho v dot dA is equal to 0. Now we can also just change it slightly, and we can write it as the surface integral of rho v dot dA is equal to minus del by del T, the volume integral of rho d omega. So this form of continuity equation tells us that the net efflux rate of mass through the control surface is equal to the rate of decrease of mass inside the control volume. Now let us have a look at simplified forms for steady flow and for incompressible flows. What will happen to this mass conservation equation? So continuity equation for steady flows. So now in this case, del by del T of anything that is equal to 0, hence our continuity equation becomes surface integral of rho v dot dA is equal to 0. Now this, let us have a look at a simple one dimensional example of a steady state compressible flow through a duct of variable cross section. So a steady compressible flow through a duct. Let us identify station 1 as the inlet. Velocity at station 1 is v1, density is rho 1, and at outlet, which we can identify as station 2, we have got density as rho 2 and velocity as v2 in x direction. The hashed part that denotes the solid boundary of the duct. Now let us apply continuity equation to this. What do we get? At the inlet, the area vector points in the direction opposite to that of the velocity, and at the outlet the velocity vector and the area vector, they are in parallel direction. So our surface integral S rho v dot dA, this can be expressed as integral over area A1 rho v dot dA plus A2 rho v dot dA. There will not be any further contribution from the side portions because that is a solid boundary. Now this rho v dot dA at station 1, that will be given as minus rho 1 v1 integral of dA over A1 plus rho 2 v2 dA2 over A2. Now let us please note that this change negative sign comes because v1 and dA1 or dA, these two v and dA vectors, they are anti-parallel at station 1. So we simply get minus rho 1 v1 A1 plus rho 2 v2 A2, and from continuity this equation this should be equal to 0, So, this gives us simplified form for one dimensional flows rho 1 V 1 A 1 is equal to rho 2 V 2 A 2. The next simpler case would be that of incompressible flows. So, what we mean by incompressible flow? In the case of incompressible flow, density is constant, that is to say it does not vary with time, and hence our del by del t integral rho dV, this becomes identically 0, and the simplified form of continuity equation becomes integral V dot dA over the surface of the control volume is equal to 0. Okay. So, now let us stop here as far as the integral forms are concerned. Now, these integral forms are important because these we require in CFD if you are using finite volume method. Next, let us proceed and derive the differential form, because that is what we would need if you want to make use of finite element or finite difference methods. Now, before we can proceed to differential form, let us see how we can obtain the differential form starting from our integral form of continuity equation. So, what was our integral form? In integral form we had two terms. First was the temporal derivative del by del t of rho dV plus a surface integral Now, let us see what happens if we had a fixed control volume, that is a control volume which does not change in time. For a fixed control volume, integration and this temporal derivative operator can be interchanged. So, thus what we can write is del by del t of integral rho dV over the control volume. This is same as the volume integral del rho over del t over dV. So, this is one part. Next we have got a surface integral. Now, let us transform this surface integral into a volume integral. Using Gauss divergence theorem, which we had looked at in the previous lecture. So, our surface integral is rho v dot dA. Now, what is equivalent volume integral? Just remember that whatever we have to the left of our dot operator, okay, we have to take divergence of that quantity. So, it simply becomes divergence of rho v dV. So, that is it. That is how now we have transformed our surface integral into a corresponding volume integral. Next we are going to put these two expressions which we just derived into our integral form. of continuity equation, if we call it as 1. So let us put this expressions 2 and 3 in our integral form continuity equation 1, and we get modified continuity equation as becomes integral over Cv del rho over del t dV plus integral over Cv divergence of rho v dV is equal to 0. Now what we have got on left hand side are two integrals over the same control volume, and hence we can easily couple these two together, and we can write this as del rho over del t plus divergence of rho v. This is what becomes our integrand. Integrate this function over the control volume Cv, and this is equal to 0. Now please remember, our choice of the control volume was arbitrary, and this integral equation, it will hold good for an arbitrary control volume if and only if that integrand function, that is the term in this square bracket, is identically 0. If that were not the case, suppose in half, what is the situation in which it can vanish? Suppose over half of the domain we had this del rho by del t plus divergence of rho v, that is equal to this particular function is positive, in other half it is negative, equal and opposite in magnitude. So that is one possibility in which case this integral can vanish. Now in this case what we can do, we can choose another control volume which is now entirely in positive half. Even then this equation must hold good, but we had assumed that del rho by del t plus divergence of rho v were positive in that half. So our assumption which we made earlier, that is wrong, that this equation can hold good only if this term del rho by del t plus divergence of rho v, this particular function, were 0 everywhere in a control volume. Okay. So that is what we say in mathematical language, that the preceding equation will hold for an arbitrary control volume if and only if the integrand vanishes everywhere, that is del rho by del t plus divergence of rho v is equal to 0, and this leads us to what we call differential form of continuity equation. The first term is the time derivative of density, and the second term is divergence of rho into v. So for compressible flows, this particular equation represents what we call transport equation for density. Now the previous vector equation can be written in Cartesian component form as del rho by del t plus del over del x of rho u plus del by of rho v by del y plus del of rho w over del z is equal to 0, where u, v and w, they represent the velocity components in x, y and z directions. Now this particular expanded equation can also be written in concise Cartesian tensor notation as del rho by del t plus del over del xi of rho ui is equal to 0, where ui represents the velocity vector in ith coordinate direction. Now what are the simplified forms which we can have of this differential continuity equation, similar to what we had earlier? Okay, now let us have a look at simplified forms of a continuity equation. Differential continuity equation. So let us have a look at the steady state flow. Now in this case del rho over del t, this would be equal to 0, hence our continuity equation becomes divergence of rho v is equal to 0. The second simplification could occur if we assume density to be constant, that is the case of incompressible flow. incompressible flow, that is our rho is constant. So now in this case del rho by del T would again be 0, and rho can be taken out and we can divide by rho, and we get the simplified form divergence of V is equal to 0. Now in this case the important point to note is the divergence of V, this what does it represent? This essentially represents the volumetric strain rate, and it is consistent with our assumption of incompressible flow, and incompressible fluid cannot be compressed. So volumetric strain rate has to be 0 in that case. So that is what this continuity equation also represents, but it also tells us one more thing, that in the case of incompressible flow our continuity equation is merely a kinematic constraint. Thus for incompressible flow the continuity equation becomes only a kinematic constraint which must be satisfied by the velocity field obtained analytically or numerically. This will have important ramifications when we come to the numerical solution of Navier-Stokes equation for incompressible flow, and that is something which we will have a detailed look at when we come to that topic. Now this differential form which we had obtained, that was based on the integral form, that we took a generalized integral form and used Gauss divergence theorem, and we obtained our differential form. We can also obtain it starting from first principle. So differential continuity equation इसको चेंज करूँगा अभी, तो ठीक है. Okay, so now let's have a look at the Cartesian coordinate system. This is a small simple differential element of length dx and dy, and let's have a look at clearly what is the mass flow which is coming in at the left plane, that is given by rho into u. Similarly, if the velocity at the left plane is rho u, this particular function rho u at the right plane can be given as rho u plus del rho u by del x dx using Taylor series expansion. Same way we can interpret this function rho v at the bottom plane and the top plane. Now let us see how we can derive our differential continuity equation using this simple Cartesian element. So let us redraw the figure again. Rho u rho v, these are the functions at negative x plane and negative y plane respectively. Their values at the center of the positive x plane will be given by Taylor series expansion rho u plus del of rho u over del x dx. Similarly, the positive y plane rho v plus del by del y of rho v dy. Now let us take one direction at a time. So what is the mass flow which enters from the left plane? So mass flow, right, entering this control volume from negative x plane. This is nothing but rho into u, and the area of this plane is dy dz. Now mass flux leaving the control volume from positive x plane, that would be rho u plus del of rho u over del x dx multiplied by the area dy dz. So can we obtain the net rate of efflux, that is net outflow, net rate of mass efflux in x direction? We will just simply subtract the inflow from outflow, and if you do that we get a very simple expression, del of rho u over del x dx dy dz. The same exercise we can repeat with respect to y planes. So similarly, net rate of mass efflux in y direction, this would be given by del of rho v over del y dx dy dz, and similarly in z direction. So now what is the net efflux from the control volume? So therefore net efflux rate of mass from differential control volume, this is equal to del u rho u over del x plus del of rho v over del y plus del of rho w over del z dx dy and dz. Now if you have to satisfy the continuity, this must be balanced by the rate of increase or the rate of change in mass in the control volume. So rate of change of mass of Cv, this would be given by del over del t of rho dx dy dz, and this must be negative of the efflux rate So if you combine these two expressions, we simply get del of rho u over del x plus del of rho v over del y plus del of rho w over del z multiplied by dx dy dz is equal to minus del rho over del t dx dy dz and thereby by rearrangement of the terms we get del rho by del t plus del over del x of rho u plus del over del y of rho v plus del over del z of rho w is equal to 0, and this is precisely the differential form of continuity equation which we had obtained earlier. So, this is yet another way in which we can obtain the differential form of continuity equation. The same exercise can be repeated for cylindrical polar coordinate system, and this I would leave as an exercise. The final equation is del rho by del t plus 1 by rho del of rho r v r over del r plus 1 by r del of rho v theta over del theta plus del of rho v z over del z is equal to 0, where v r, v theta and v z, these are the velocity components in r, theta and z directions respectively. So, please take a small differential cylindrical polar control volume and complete this derivation following the steps which we used earlier with rectangular coordinate system. The next exercise would be derive continuity equation in a spherical polar coordinate system. Once again, choose a small differential element in spherical polar coordinates. In both of these polar coordinates, please be aware of the changes in area across different r positions in your derivations. So, that is why we are going to now put a full stop to this lecture on continuity equation, and in the next lecture we will take up the derivation of momentum equation.